In this Quantixy video, we will illustrate that the twin paradox is a famous scientific thought experiment. It describes a strange situation where two identical twins experience time in very different ways. One twin stays on Earth, living a normal life. The other twin climbs into a spaceship and travels through space at an extremely high speed, close to the speed of light. Now, here's where things get weird. When the traveling twin finally returns to Earth, they are younger than the twin who stayed behind. Same parents, same DNA, different ages. This doesn't happen because space is magical. It happens because time itself is flexible. According to Albert Einstein's theory of relativity, time slows down for objects moving very fast. The faster you move through space, the slower time passes for you. So while the Earth twin experiences time normally, birthdays, aging, and back pain, the space twin's clock is ticking more slowly. And this isn't just a theory. Scientists have tested time dilation using ultra-precise atomic clocks. Clocks on fast airplanes and satellites actually run slower than clocks on Earth. Now you might wonder, if motion is relative, shouldn't each twin see the other aging slower? Great question. The answer is acceleration. The traveling twin has to speed up, slow down, turn around, and come back. The Earth's twin doesn't. That change in motion makes all the difference. So the paradox isn't really a paradox at all. It's a real effect of how space and time work together. The twin paradox shows us something incredible. Time is not the same for everyone. If humans ever master near light speed travel, space travel could become a one-way trip to the future. You might explore the universe, but come back younger than your own twin. And that's the twin paradox proof that in our universe, time doesn't just tick, it bends. At first, this result completely shocked scientists because, according to common sense, motion is relative. If you're on a train and it's moving, it feels normal to you. But to someone standing outside, you're the one speeding by. So if motion is relative, shouldn't each twin see the other as the one who's moving? That's where things get confusing. From the traveling twin's perspective, Earth is rushing away at incredible speed. So logically, the Earth's twin should age more slowly. But from Earth's perspective, the spaceship is the one moving. So the space twin should age more slowly. Both sides seem correct, and yet only one twin ends up younger. That contradiction made the whole idea seem impossible. Physicists argued over it for years. Some even thought Einstein's theory must be wrong. So why doesn't each twin end up younger from their own point of view? Here's the twist. The situation is not symmetric. The traveling twin doesn't just move, they accelerate, slow down, turn around, and come back. The Earth's twin stays in one steady frame of motion the entire time. That change in speed breaks the balance. Acceleration is what separates the two experiences of time. So even though motion can be relative, changing motion is not. Once scientists understood this, the confusion disappeared. The paradox wasn't a mistake, it was a lesson. A lesson that time and motion are deeply connected, and our everyday intuition isn't built for near light speed travel. That's why it's called the twin paradox, not because it's wrong, but because it sounds impossible. The twin paradox emerged from the theory of relativity in the early 1900s, a time when physics was about to get very weird. Before this, scientists believed time was absolute. One universal clock for the entire universe. Tick, tick. Same for everyone. Then came Albert Einstein. In 1905, Einstein introduced the special theory of relativity, and suddenly, time was no longer fixed. It could stretch, slow down, and depend on motion. Physicists began asking a dangerous question. What actually happens to time when you move incredibly fast? As scientists explored this idea, they realized something shocking. At near light speed, time behaves differently for different observers. That's when the twin paradox was born. It wasn't designed as a real experiment. It was a thought experiment meant to test the limits of relativity. No spaceships required, at least not yet. At first, many physicists were uncomfortable with the result. The idea that two people could experience different amounts of time felt impossible. Some even thought relativity had broken logic itself. But as math, experiments, and real-world measurements improved, the paradox didn't disappear, it became stronger. Atomic clocks, particle accelerators, and satellites all confirmed the same thing. Time really does slow down at high speeds. What started as a strange idea on paper turned into one of the most important discoveries in modern science. The twin paradox didn't just change physics, it changed how humanity understands reality itself. Time is not universal, it's personal, and that single realization reshaped everything from space travel to GPS to how we think about the universe. Not bad for a paradox, right? The paradox is rooted in Einstein's special theory of relativity, a theory that quietly rewrote the rules of the universe. Before this idea, scientists assumed time was fixed. One giant cosmic stopwatch, ticking the same for everyone, everywhere. Einstein showed us something shocking. Time is not fixed. According to special relativity, space and time are connected. You don't move through just space, you move through space-time. And here's the wild part. The faster you move through space, the slower you move through time. This effect is called time dilation. At everyday speeds, walking, driving, even flying, the effect is tiny. So tiny that you'll still be late for school or work. But as you approach the speed of light, time begins to slow dramatically. If you could travel at 90% the speed of light, your clock would tick much slower than clocks on Earth. At 99.9%, time nearly crawls. From your point of view, everything feels normal. Your heart beats normally. Your watch ticks normally. But back on Earth, years are flying by. So when the traveling twin returns, they haven't cheated time. They experienced less of it. No magic, no time machine. Just physics doing something very rude to common sense. The twin paradox teaches us a powerful lesson. Time is not something we all share equally. It depends on how fast you move. So next time you feel like time is moving too fast, don't worry. Unless you're traveling near the speed of light, it's not Einstein's fault. This effect is called time dilation. And no, it's not a metaphor. Time doesn't feel slower. It actually is slower. For the traveling twin, time physically slows down. Their clock ticks more slowly. Their aging slows down too. Not because of biology, not because of special space vitamins, but because time itself moves differently for them. Here's the strange part. From the traveler's point of view, everything feels completely normal. Their heartbeat is normal. Their watch ticks normally. They don't notice anything unusual at all. But when they look back at Earth, they see Earth's clocks racing ahead. Meanwhile, from Earth's perspective, the spaceship is moving incredibly fast. And that motion causes time on the ship to slow down. Both perspectives are correct. That's the weird beauty of relativity. Time dilation happens because the speed of light is constant. No matter how fast you move, light always moves at the same speed. So something has to give. And what gives is time. Scientists have proven this effect many times. Subatomic particles created in the atmosphere survive longer when moving fast. Atomic clocks flown on airplanes fall behind clocks on the ground. Time dilation isn't science fiction. It's measured, it's tested, it's real. So when the traveling twin returns home, they didn't pause aging, they simply experienced less time. The twin paradox shows us that time isn't just something we watch, it's something we move through. And the faster you move, the less of it you get. Which sounds amazing, until you realize everyone you know got older without you. Have you ever heard of the twin paradox? It's a mind-bending idea from Einstein's theory of relativity. Imagine two identical twins. One stays on Earth while the other zooms off in a super-fast spaceship, travels near the speed of light, and then comes back. When they reunite, the space-traveling twin is much younger than the one who stayed home. But wait, from the traveling twin's perspective, wasn't it the Earth that was moving away and coming back? Why isn't the Earth's twin younger? It seems like a contradiction, right? Well, the secret isn't just about speed, it's about acceleration. The twin on the spaceship doesn't just move fast. They have to launch, speed up, slow down, turn around, and then accelerate again to come home. That's a whole lot of changing speed and direction. The Earthbound twin. They just hang out on Earth in a relatively constant state of motion. In physics, this difference is everything. While constant speed can be relative, acceleration is absolute. You feel it. It's the force pushing you back in your seat when a car floors it. Because the traveling twin is the only one who accelerates and changes their frame of reference. The symmetry is broken. Their clock is the one that actually slows down dramatically. So the twin paradox isn't a paradox at all. It's a profound demonstration of how time works. Time isn't the same for everyone. It depends on your path through space-time. It's a lesson that motion, especially accelerated motion, literally changes how you experience time. So, if you're looking for the fountain of youth, you might just need a really, really fast spaceship. This is not just theory. Time dilation isn't some abstract idea in a physics textbook. It's real. Precise experiments have measured time slowing down at high speeds. Atomic clocks flown on airplanes tick more slowly than identical clocks on the ground. Tiny differences, yes, but measurable. And scientists can actually see time behaving differently depending on motion. Even modern technology depends on this. Take GPS satellites, for example. These satellites zip around Earth at incredible speeds, and they're also farther from Earth's gravity. Both motion and gravity affect their clocks. If engineers didn't correct for time dilation, your GPS would be miles off. You'd end up navigating to the neighbor's driveway instead of your own. And it's not just satellites. Particle accelerators, which smash particles close to the speed of light, rely on time dilation too. Particles that normally decay in microseconds live longer when they move fast, exactly what relativity predicts. So yes, the twin paradox has been experimentally verified. It's not a thought experiment anymore. It's real physics. It's kind of amazing, right? Something that sounds like science fiction, twins aging differently because of space travel, is actually part of our modern, technology-driven world. So next time you hear someone say, Einstein was crazy, you can smile and say, no, he was just ahead of his time. Literally. The twin paradox shows us that the universe doesn't always follow our intuition. Time is flexible, motion matters, and reality is far stranger and cooler than most of us imagine. Have you ever wished you could travel into the future? Well, for astronauts, it's not science fiction, it's a real side effect of their job. This is the fascinating world of time dilation. According to Einstein's theory of relativity, the faster you move, the slower time passes for you compared to someone stationary. Astronauts on the International Space Station are orbiting Earth at a mind-boggling speed of 17,500 miles per hour. While that's incredibly fast, the effect on time is tiny, but measurable. For every 6 months they spend in space, they age about 0.005 seconds less than us back on Earth. So, when they return, they've effectively traveled a fraction of a second into our future. Astronaut Sergei Krikalev holds the record for the most time spent in orbit, a total of 803 days. Because of this, he is about 1/48th of a second younger than he would be if he had stayed on Earth. It might not sound like much, but it proves that time travel, even on this minuscule scale, is possible. As we venture further into the cosmos and reach even higher speeds, who knows how much further into the future we could go? The universe is full of wonders, and time is one of its greatest mysteries. The twin paradox didn't just bend minds, it revolutionized science. It changed the way we think about time, motion, and the universe. And the impact isn't just theoretical. It's all around us, every day. Take GPS, for example. Without accounting for time dilation, your phone would think you are miles away from your actual location. Every text, map direction, and navigation alert relies on these tiny differences in how time flows. Or consider space travel. Satellites, space stations, and even interplanetary missions rely on Einstein's insights. Without understanding how time moves differently at high speeds, astronauts could be seriously miscalculating their orbits. Let's just say, we'd be sending astronauts into the wrong side of the moon. Precision timing in physics. Absolutely dependent on this. Particle accelerators, atomic clocks, and experiments at near-light speeds all rely on the effects predicted by the twin paradox. Even your favorite scientific breakthroughs, from quantum mechanics to relativity tests, wouldn't be as precise without it. In short, without understanding time dilation, modern technology as we know it would fail spectacularly. We wouldn't have reliable navigation, accurate communications, or advanced space exploration. And the funny thing? It all comes from a paradox that sounds like science fiction. Twins aging differently because of motion through space. Einstein probably didn't imagine that his thought experiment would literally guide your phone's GPS every day. So next time you use a map app or watch a satellite zoom overhead, remember, the twin paradox isn't just a mind-bending physics concept. It's the reason we can explore, navigate, and understand the universe with precision. Science may bend time, but it also bends reality in ways that touch everyone, whether you're on Earth or orbiting above it. However, the twin paradox also reveals some harsh realities. Sure, it's fun to imagine zooming through space, aging slowly while everyone else gets older. But the truth is, reaching near light speed is incredibly hard. We're talking about unimaginable amounts of energy. Faster than anything we can currently produce. It's faster than any rocket ever built. Basically, if you tried it with today's technology, you'd run out of fuel before leaving the solar system, and probably set off a few physics alarms along the way. And let's not forget our bodies. Human beings aren't exactly built for near light speed travel. The acceleration alone would feel like riding every roller coaster in the world at the same time. Bone, muscle, blood flow. Your body would get a very rude awakening. Radiation from space. Yeah, that's another problem. No spacesuit in existence can fully protect you from the cosmic rays that come with such speeds. So for now, interstellar travel is mostly science fiction. It's with a hint of reality check, science. But here's the funny part. Even if we can't go that fast yet, the twin paradox still applies to every moving object. Planes, satellites, particle accelerators, they all experience tiny bits of time dilation every day. So while we may not have warp drives or light-speed spaceships, humanity is still experiencing the paradox in small, measurable ways. Time travel to the future. Already happening, just not in a flashy sci-fi movie style. The twin paradox teaches us both the limitless possibilities of physics and the very real limits of human technology. It's a cosmic reminder. The universe is stranger than fiction. And it doesn't care about our comfort or convenience. In the future, a deeper understanding of space-time may unlock incredible possibilities. Imagine propulsion systems so advanced that we could approach near-light speeds without frying our engines or ourselves. Time dilation wouldn't just be a mind-bending physics idea anymore. It could become a practical tool for exploring the galaxy. Long journeys to distant stars. No problem if time slows down enough for the travelers. They could make the trip and return safely without aging decades while Earth continues on. It's like hitting the ultimate fast-forward button for humans. Of course, there are still huge challenges. Energy requirements, radiation, and the stresses of near-light speed travel are enormous hurdles. But physics is giving us the blueprint. And when humans finally figure it out, interstellar travel might not just be science fiction, it could be science fact. Here's a fun thought. You could hop on a spaceship, travel to a star system hundreds of light years away, come back, and all your friends on Earth would have aged decades while you're still the same age. You'd be the ultimate cosmic Benjamin Button. Even now, the twin paradox teaches us a profound lesson. Time isn't a constant. It's flexible. It bends with motion and gravity, shaping how we experience reality. And as our technology improves, as we push the limits of energy, propulsion, and biology, we might one day use time dilation to explore the stars safely, taking humanity further than ever before, while keeping our bodies young enough to enjoy the adventure. The twin paradox is more than a puzzle. It's a glimpse into the future of space travel. A reminder that the universe is stranger, cooler, and funnier than we often imagine. Our story today was just a small glimpse into the fascinating world of modern scientific research. At QuanticC, we bring modern scientific discoveries to you in a way that's easy to understand, fun, and educational. No complicated jargon, no boring lectures. Just amazing science explained clearly, with a dash of humor for good measure. Today, we dove into the twin paradox. And what did we learn? The twin paradox is more than a thought experiment. It proves that time is flexible, real, and deeply connected to the universe. It shows us that aging, motion, and time itself are not absolute. They depend on how we move through the cosmos. As science advances, our understanding of time may continue to evolve. Someday, humans might travel near the speed of light. Satellites, particle accelerators, and futuristic spaceships will bend time in ways that sound impossible, but are completely real, thanks to Einstein and the paradox that bears witness to it. So remember this: time isn't just ticking away on a clock. It's personal, it's dynamic, it's part of the fabric of the universe, and it shapes everything we do, every moment of our lives. If you enjoyed this journey through space-time, make sure to stay with QuanticC. Because together, we'll explore the strangest, most amazing and mind-bending discoveries that science has to offer. And maybe, just maybe, bend your understanding of reality a little bit too. So until next time, keep looking at the stars, keep asking questions, and remember, the universe is stranger, funnier, and more incredible than we ever imagined.